Hello, welcome to this class. Today we will talk about the electrical current and DC circuit. This is a lecture for week 11th for the international class in IPB University. The learning outcomes for this class: once you finish this class, you would be able to determine the electrical current, the resistance, electrical energy and power, the equivalence resistance of a simple DC circuit, analyze a closed circuit composed of several closed loops. So, what is current? Electrical current is actually the total amount of charges that pass a particular area A in a period of time delta t. So you can look at this picture. If we have a cross-sectional area A and you count how many charges or electrons pass this area in a particular time, that's what we call as a current. So simply current is just the rate of flowing charges. I is equal to delta Q divided by delta T. The unit for current is ampere. Conventionally, current is assumed as the flowing of positive charge. When a potential difference or voltage, for example from a battery, is applied to the ends of a particular metal conductor, the amount of current flowing in a conductor is proportional to the voltage applied. I is proportional to the delta V. The ratio of voltage to current, delta V divided by I, is equal to R, or resistance. This is called as the Ohm's law. So you can see in this picture below, so you connect the conductor with the battery, then you measure what is the change of current as a function of delta V. When you change the potential delta V, you will measure the current here. Ohm's law first formulated by George Simon Ohm when he studied the electrical behavior of some metals or some materials. So he formulated this equation, this famous equation, delta V equal to IR. Means that if you change the potential gradually, so you will see the increasing of current flowing into the material. And if we have what we call as ohmic material, we will have a straight line like this. Of course, between one metal and other metal, they will have a different slope. And the slope here is actually tell you about the conductivity, or 1 over R. So the resistance of the material is actually the inverse of this slope. Other materials like semiconductors, like a ceramic, have a different behavior. Instead of a straight line, you will find more like exponential like this. We call this material non-linear material. We call this also non-ohmic material. The flowing of electrons in a conductor is scattered by the collision or interaction with other atoms in a solid or crystal lattice. This is the origin of resistivity. So when the temperature is very low, the vibration of the atoms in a solid or in a crystal lattice, the vibration is very slow. In this case, when the electrons flowing into this material, it will find less resistance. But if you increase the temperature of the material, the vibration of the atom will become faster and faster. The movement of the electrons will be disturbed, or electron will be scattered. In this case, we find more resistant or more resistivity in this material. The resistance of a particular material is proportional to the length of the material and the type of material, and inversely proportional to the cross-sectional area of the material. Rho, or the resistivity of material, is depend on the type of material. So the resistivity of iron, the resistivity of steel, the resistivity of aluminum, bronze, they will be different. Conductor has a low resistivity, insulator has a high resistivity, and resistivity also depend on the temperature. When you increase the temperature, the vibration of the atomic crystal will be higher. So this will create a disturbance to the flowing electrons. So when you have a higher temperature, the resistivity will increase. And the equation is like this: rho as a function of temperature at a particular temperature is equal to rho naught. This is the specific resistivity of a particular material, times 1 plus alpha delta T, or T minus T naught. Alpha is the temperature coefficient of resistivity. So the resistance as a function of temperature is simply just R equal to R naught 1 plus alpha delta T. The resistivity of some materials shown in this table. If you take a look at this table, for example, for some metals like silver, copper, gold, aluminum, they have a different resistivity. In this case, silver has the lowest resistivity as compared to copper, gold, and aluminum, with only 1.61 10 to the minus 8 ohm meter. Other materials, including ceramic and water liquid, also shown in this table. Due to collision between electrons and solid crystal, some of the electrical energy carried by electrons will be converted into thermal energy. This process is called as a dissipation, and this dissipation can be found, for example, in light bulb, iron heater, toaster, or toaster filaments, and other things. The rate of this energy conversion from electrical energy into thermal energy is known as power, in this case electric power, in the unit of joule per second, or watt. P is equal to delta E over delta T. P is the rate of conversion energy from the electrical into thermal. And we know that delta E is equal to delta V times I times delta T. And from Ohm's law, we can write this down as P equal to delta V squared divided by R, or I squared times R. How to measure current and voltage? To measure current, we have to break the circuit, then insert the ammeter or the current meter. So if you have this circuit like this, for example, we have battery and resistor here. You want to measure the electrical current flowing in this circuit, you have to break it and let the current flowing into the ammeter. For measuring the voltage, you don't have to break the circuit. What you need to do is just connect the two probes from the voltmeter to the point that we are interested in. For example, if we have a simple closed circuit like this, consisting of battery and resistor, and you want to know what is the voltage between point A and B, so you just connect the probes to point A and point B. Then you measure the voltage. A simple DC circuit consists of DC voltage source, for example a battery, and then electrical device, for example resistor, and a closed circuit. The delta VAB, the potential difference between point A and B, is simply just I, the current flowing into this closed circuit, times R, the total resistance in this circuit. And you can avoid short circuit, means connection without resistor or very small resistance. And for a high voltage, you also need to use a circuit breaker for safety. Battery is a device that converts a chemical energy into an electrical energy. So inside the battery we have several materials, for example zinc and also carbon paste. So in principle we have two types of materials, one consisting more electrons and the other one less electrons. And when you connect the positive pole and the negative pole through a closed circuit, you will see the flowing, you will find the flowing of electrons or the current inside the closed circuit. Once everything is paired, means that there is no more voltage difference, potential difference between the positive and negative pole here, so your battery is dead. Battery generates a potential difference which is called as an electromotive force, E, epsilon, with the internal resistance R. The internal resistance R is increased as the duration use of the battery. The terminal voltage VAB that we actually use in our device is VAB is E, the electromotive force, the initial potential difference in the battery, minus I times R. R is the internal resistance of the battery, or E equal to IR, big R, plus IR, small r. We can have two different connections of resistor in a closed circuit. First, we talk about the series connection of resistor. If you have a closed circuit like this, consisting of one battery, plus minus here, and then you have two resistors, R1 and R2, they are connected in series with the battery. In this case, the potential from the battery is distributed to resistor 1 and resistor 2. So V total from the battery is V1 plus V2. And from the Ohm's law, we know that V equal to IR. So we can rewrite this equation V as I times R. I total times R total. V1 is I1 times R1. And V2 is I2 times R2. Remember, in a series circuit, the current flowing in every point here in the closed circuit will be the same. So there is no branch. It means that all the current here are the same everywhere in this closed circuit. It means that I total from the battery equal to I in the resistor 1 or I1 equal to I2, the current in resistor 2. Since I equal to I1 equal to I2, then we can cross them out in the equation above. IR equal to I1 R1 plus I2 R2. You can cross I2 I1 I out. So we end up with R equal to R1 plus R2. So the equivalent resistance, a single resistor that replace the two resistors here is simply just R1 plus R2. If you have more, suppose until N, so the equivalent resistance of a series connection of resistor is R1 plus R2 plus blah 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 plus Rn. A series connection of resistor is also known as a voltage divider circuit, since by having this resistor now you have different voltage at each point. You have V1 in R1 and you have V2 in R2. The parallel connection of resistor. If you look at this picture below, you have a parallel connection of resistor. What is parallel connection? Suppose the beginning of the resistor is called as a tail and the end of the resistor is called as a head. So in parallel connection, we connect the tail of R2 with the tail of R1 and connect it with a positive pole of the battery. We connect the head of R2 and the head of R1 to the negative pole of the battery. So this is called as a parallel. So you connect head with head and tail with tail. In this case, I equal to I1 plus I2. Why? If you have a parallel connection here, actually you divide the current. The initial current I, now you have a junction here. And this current will be splitted into I1 goes to R1 and I2 goes to R2. But then after flowing into each particular resistance, it will goes back combined together. I2 plus I1 goes back to I. So a parallel connection of resistor is also known as a current divider circuit. So I equal to I1 plus I2. And remember from the Ohm's law, I equal to V divided by R. So we can write I here, I total here as a V divided by R equal to I1, which is V1 divided by R1 plus I2 or V2 divided by R2. Since V equal to V1 equal to V2 in a parallel circuit, the voltage everywhere is the same. So in the tail of R2, in the tail of R1, and in the battery, the voltage are the same. So we have V equal to V1 equal to V2. We can cross the V outs. So we end up with 1 over R equal to 1 over R1 plus 1 over R2. So the parallel equivalent resistance is 1 over R equivalent equal to 1 over R1 plus 1 over R2, blah 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 until 1 over Rn. A simple closed circuit must follow the Kirchhoff's law. We have two Kirchhoff's law, the first Kirchhoff's law and the second Kirchhoff's law. In Kirchhoff's first law, the total incoming current to a junction is equal to the total outgoing current. So if you look at this picture, the incoming current with the red color here, IA and IB, they are the incoming current, has to be equal with the outgoing current, which is IC and ID. So it's just simply as that. The total current goes into the junction has to be equal with the total current out from the junction. The Kirchhoff's second law corresponds to the conservation of energy. Energy is related to the voltage or potential difference. So in a Kirchhoff's second law, the total voltage from the battery must be equal to the total voltage that you find in resistor 1, resistor 2, and so on. So we formulate this Kirchhoff's second law as sigma E plus sigma IR equal to 0. Or in a closed loop, the algebra summation of the electromotive force from the batteries and the potential change in the loop is 0. Here are some rules for solving the problem of a closed circuit using Kirchhoff's law. First, you have to look at the loop and first choose a loop and then choose the direction of the loop. The sign of current is positive if the direction of the current is the same with the direction of the loop. The sign of current is negative if in the opposite direction of the loop. If the arrow of the loop's direction hits the positive terminal of the battery, then use a positive sign for this voltage. If the arrow of the loop's direction hits the negative terminal of the battery, then use a negative sign for this voltage. This is the example of how to use Kirchhoff's law. Suppose we have a single loop like this. We have to define the direction of the loop first. In this case, the direction of the loop is already chosen following the red arrows. According to the Kirchhoff's second law, sigma epsilon plus sigma I times R equal to 0. When the red arrow hits the battery 2 or epsilon 2, the red arrow hits the positive pole, so E2 is positive. And when the red arrow hits the battery 1, epsilon 1, the arrow hits the negative pole first, so epsilon 1 is negative, E2 minus E1. And we only have a single current I, and the direction of the current here is in the same direction with the red arrow, so I is positive. So we can write this down, epsilon 2 minus epsilon 1 plus positive I times R1 plus R2. What about if we have a two-loop circuit instead of one? So here are some of the rules that you can use. First, you have to determine the currents, their labels and direction in a junction. And then you have to use Kirchhoff's first law to write down the equation of current. So for example, in this case, you have I equal to I1 plus I2. And then you determine the direction of each loop. Then you write down the equation of voltage using Kirchhoff's second law in each loop. And using algebra technique, substitution and elimination, you combine all equations from each loop and solve for the currents. This is the example of how to use the Kirchhoff's law in two-loop circuits. First, we draw the direction of the loops in each loops. And using the Kirchhoff's first law, equation of current, the total incoming current at the particular junction has to be equal with the total outgoing current from that junction. So if we look at the point E here, A, B, C, D, E, F. So look at point E. At junction E, the total incoming current I equal to the outgoing current I1 and I2. So we can write down I equal to I1 plus I2. And using Kirchhoff's second law for the loop number 1, we've already defined the direction of the loop following the red arrow on the left side. The arrow hits the negative E1, the negative epsilon 1. So we have minus epsilon 1 plus I times R1 plus I1 R2. Since the direction of I1 is in the same direction with the direction of the loop at loop 1. So we have a positive I1 times R2. And this is equal to 0. And for loop 2, we have a different direction of loop like this. And the red arrow hits the positive pole of E2, so we have positive epsilon 2, and then we have negative I1 because the direction of the I1 is in the opposite direction to the loop, to the direction of the loop number 2, so minus I1 times R2, but the direction of I2 is in the same direction with the direction of the loop at loops number 2. So plus I2 times R3 equal to 0. Solving those three equations, then you can find what you're looking for. This is some example, problem 1. Suppose you have a flashlight that powered by 3-volt battery and 0.4 ampere current flows in the series circuit inside. Find a power distributed to the light bulb and B, the total amount of dissipated energy of the light bulb in 5.5 minutes. So using the power equation, P equal to I times V, so you can have the value of the power. P is 1.2 watt, and for the energy, dissipated energy, simply just the power times time. 1.2 watt times 5.5 minutes converted into second is 330 seconds. Then you can get the result. The total dissipated energy will be 400 joule. For problem number 2, suppose you have a series connection of resistor. The resistor 1 is, the resistance 1 is 6 ohm, the resistance 3 is 3 ohm. Find the amount of current flowing in that circuit. I is equal to V divided by R, and R here is the R total. The R total, the total resistance of a series connection of circuit is simply just the algebra summation of the resistor. So 6 plus 3 is 9. So I will be V, which is 12 volt divided by 9 ohm. That would be the current. So this is how you solve the problem. You have this circuit, the series connection of resistor. So to find the equivalent resistance, you just need to add them up. 6 plus 3 equal to 9 ohm. The total current flowing into that equation is V divided by R equivalent, 12 volt divided by 9 ohm, or equal to 1.33 amps. To find the dissipated power in resistor 1, in 6 ohm resistor, P is simply I squared times R, or 1.33 amps squared times 6 ohm. So you end up with 10.67 watt. This is the amount of dissipated power at resistor 1, 6 ohm. And the total dissipated power at resistor 2, or the 3 ohms here, P is equal to I squared R, 1.33 amps squared times 3 ohms equal to 5.33 watt. So the total dissipated power at this circuit is simply just the summation of the dissipation power at resistor 1 and 2. So you end up with the total dissipated power of 16 watt. If you have this kind of circuit, suppose you have a battery 24 volt connected in series with 110 ohms, and then you have a parallel connection 180 and 220, 250 ohms. You have to find the equivalent resistance of the circuit above. Means that here you have 4 resistors, so you are asked if these 4 resistors will be replaced by a single resistor, what we call as a equivalent resistance. What is that? What is the equivalence resistor of this circuit. To solve that problem, we have to break up the circuit one by one. First, you look at the series connection here. 220 and 250, they are connected in series, so you can replace this by a single resistor, which is 470. Now you have 470 ohm and 180 ohm. They are connected in parallel, so you can find the equivalent resistance, the parallel equivalent resistance of 180 and 470. So you end up with 130 ohm. Finally, now you have 130 ohm connected in series with 110. Then you find the answer here, 240 ohm. The equivalent resistance of this circuit is 240 ohm. In this problem, you have two loop circuit. So the epsilon 1 16 volt, epsilon 2 8 volt, R1 is 12 ohm, R2 6 ohm, R3 6 ohm. You have to find the current flows in R2. Since you have more than one loop, so you need to use Kirchhoff's first law and Kirchhoff's second law. So first you need to define the direction of the loop as shown by the red arrow here. And for the loop 1, the red arrow hit the negative pole of epsilon 1, so we have minus epsilon 1, and also hit the negative pole of E2, so you have minus epsilon 2 here, and you have I times R1, and also I1 times R1 equal to 0. Yeah. All the rest just math. For the loop 2, you choose this direction of loop. So when the red arrow of the loop hits the epsilon 2, it hits the positive pole, so you have positive epsilon 2, and also hits the positive pole of epsilon 3, so epsilon 2 plus epsilon 3, and the direction of I1 is in the opposite direction with the direction of loop number 2. So you have minus I1. Minus I1 meets with R2. And what about I2? The direction of I2 is in the same direction with the loop number 2. So plus I2 times R3. So having those two equations, then you can simply just use algebra to solve for the current flows in R2. Okay, thank you very much. That's resume our lectures today, and next week we will talk about the magnetism. Okay, thank you very much.